Okay. All right. So let's talk about this one. This is a very famous demonstration of the difference between electronic codebook and cipher block chaining modes. Now, block ciphers like AES. AES is the government-approved cipher that we're supposed to be using for everything, pretty much. Anytime you can get away with private key encryption, where you have to have the same key from the sender and the recipient. And it's used by almost every protocol. The problem is, I mentioned before, Zcash, one of the most advanced cryptocurrencies, was written by a high school dropout with no formal training at all. And he had a basic rule, which is never use any code written by a college professor for anything, because college professors do the simplest case just to prove a concept, and they don't pay attention to all the practical problems that matter in real production, like making something that can handle a lot of load, that can scale to a lot of servers, and that doesn't have error cases that cause problems. And so the standard encryption that people do in colleges is often called textbook encryption. And the thing about it is it has serious flaws. And so this is what's called electronic codebook mode. So let's start with this. I wonder if I have to install PyCryptoDome. I probably do. So to execute this line in command line in a Google book like this, what you do is you put an exclamation point in front of it. That'll execute a shell command. So that should install this PyCryptoDome library, which is a nice modern one that has the encryption routines I need, in particular AES. Looks like that's working. So now we'll encrypt the image. This is going to create a new cipher object. All right, and I think I'm going to, okay, we got it. Now it's going to be a little bit funny. I wrote that with a local install of Python, and I'm trying to do it now in this online system just to make it better. This will create a new cipher object. That's how you import it. And I just use a key. The key has to be 16 bytes long, so I just use 4 A's, 4 B's, 4 C's, 4 D's. And this creates a cipher object that we can play with. Now, I'm going to load this tux file, so I have to upload this image. So I'm going to right-click and save image. I'll put it in my downloads. All right. tux.bmp. And now I'm going to upload it into this environment, which you do here. There, upload. There we are. And there it is, tux. Good. So now I have tux.bitmap available locally in this Google Cloud Python environment. Now I can encrypt the image, and that's what this is going to do. This is going to open tux.bitmap, read it as binary, and it's going to put it in a variable called clear. All right. All right, it's done. I didn't print anything out, so we can't see it, but it read the file and it put all the bytes in a object called clear. Now I'm going to encrypt it. This will make ciphertext out of it using the key I specified earlier. So now there's going to be a ciphertext object. It doesn't like that. Error. And see, here's what you expect. The problem with this is the length is not exactly a multiple of 16 bytes. And that is the fundamental problem here. If you have a block cipher like AES, it encrypts 16 bytes at a time. Well, what if you have 17 bytes? Then you have to somehow pad the block and fill it up. And there are various ways to do that. These will show us our length problem. If I do this, let's just go make another block here. There. Okay, the length of clear is didn't print for some reason, but that's interesting. Let me just put a print here then. In immediate mode, Python usually does print without having to put in the word print, but here it only did it the second time and not the first time. So like I say, this cloud Python environment is a little screwy. Control E should take me to the end of that line, and it does. There we are. Now it's going to print both of them. There. So this is the length of clear, almost a megabyte. And the problem is it's not an integral multiple of 16. It's some number of 16-bit blocks and 2 extra bytes at the end. So what we're going to do is make a trimmed version, which skips the first 64 bytes and the last 2 bytes. So I get most of the data. And the reason I'm doing this is I want to actually view the image. And the way bitmap images work, there's some header information not shown here. And all this is color information. So I want to encrypt all the visible color information without destroying the header information. And I'm going to skip the last 2 bytes down there because the last pixel can be a little off and I don't really care. So this clear trimmed quantity is going to be an integral multiple of 16 bytes now. And I can encrypt that without having to implement a padding scheme, which I don't want to bother with. So that creates the thing called clear trimmed, and we can see it. We can print it and see it. This is going to work now. If I go here, and I have to put in the explicit print commands for some reason in this environment, which is a little rude, but you can't have everything. And I got to put the closing parentheses on these. There. Now it should be able to show me the new length. There's the length, and now there's no remainder when dividing by 16. So the clear trimmed is in blocks, and I can make ciphertext out of that. And it won't fail with an error message. So now I've got ciphertext. Now I'm going to make a visible image, and here's how it works. I take the first 64 bytes of the clear, so I'm going to have the bitmap header uncontaminated, and then put in the ciphertext, and then put in the last 2 bytes of the clear again. So the main body, the visible part of the image, will be encrypted. And now I'm going to write it as tux electronic codebook.bitmap and write it out. So this should work. It's done. And now if I look, I have tux ecb.bitmap, and I should be able to download this. Yeah, download, good. And I guess here it is, okay. It's somewhere, perhaps my downloads folder. Yes, in my downloads folder, which is on a different screen. Okay, and the point is, here's the original tux. If I double click it, it will open in some kind of viewer. Okay, there it is in the default viewer. And the encrypted one is here. If I double click that, that's what I get. And this is why this is a very famous demonstration. The problem is this is textbook encryption. It took each group of 16 bytes and encrypted it. So it took some data from here and encrypted it. And then the next block was exactly identical. White is FFFFFF. So all this white region is just a whole bunch of bytes that are all FFFFFF. So each one of them encrypts to the same pattern here. So even though you've encrypted it, this is not what the goal is. It has not concealed the significance of the image. This is the problem with textbook encryption. Repeated bytes of input data produce exactly identical output data, and therefore it doesn't accomplish the goal of concealing the image. So this is a serious problem. And everybody became aware of this, and electronic codebook mode called textbook encryption was considered to be a bad technique for this reason. And so they developed a solution, and the solution is cipher block chaining. This is the technique that was intended to fix this. So in cipher block chaining, you have an additional initialization vector, which is combined with the input first. So I'm going to just make a new notebook here. I'm going to close this sidebar stuff. I think I'm not going to make a new notebook because I might lose that. I'll just keep going because I don't want to lose that file. All right. So let's, here's the IV. All right. So I'm going to make a new cipher object using AES mode CBC. And in cipher block chaining, you have not only the key, you have another 16-byte quantity called the initialization vector. And let me get the, I'm going to need this anyway. I'm going to skip to a project ahead so I get a useful figure here. This one here, so you can see how this works. Okay, this is how it works. The initialization vector comes in, you have the plain text come in, then you encrypt it with the key, and that makes a block of ciphertext. Then you take the block of ciphertext here and use that as the initialization vector for the next block. And then you take this output and use it as the IV for the next block. That's why they call it chaining. Each block of encryption produces the pseudo-random stuff that's used for the next block. I must say, when I first heard that you use the output of one block as part of the input for the next block, this made me nervous with good reason. This does lead to a weakness. However, it solves the immediate problem, which is that patterns are preserved in the output. So that's cipher block chaining, and that's what we're going to implement here. So now we've made this is the encrypted stuff. So all we have to do is the same kind of output. We're just going to write out the unencrypted first 64 bytes, then the ciphertext encrypted with the other system, and then clear at the end, and we're going to call that tux CBC. So let me get that and put it here and run it. Okay, now there should be another file called tux CBC for cipher block chaining. When I download that, it should be here. And that one, wait, I did something wrong. Okay, that looks just the same, so I must have done something wrong. Let's go back to my code. Oh, I skipped a block here. I didn't actually do the encryption. To do the encryption, I needed to do this. I skipped this line. That'll do it. So let's encrypt it with the new system and now write it out again. I'm going to call it CBC2. All right. Yes. I'm not seeing it. I've run this. I don't see an error message, but it's not there. Oh, there it is. It was just slow. Okay, cbc2.bitmap. Okay, download and view it. There we are. Now I get what you want from encryption. Just total snow everywhere, all the patterns gone. So this was considered a big step forward, and cipher block chaining became the recommended technique. So that's the original step forward. That's the first thing I want to show you. So I'm going to stop this video.